Okay, so I'm going to do the solution for team challenge number 18. I'm not going to do number 19 because it's essentially the same with different numbers, but I'll walk through 18 very carefully. Okay, so in this question, you're given some information in the question and on a chart that you have to get the correct pieces of information from. So it asks you to look at the total number of moles of ATP that you would get from the complete oxidation of the fat and sugar in this thing. This was a McDonald's triple chocolate shake. Okay, so the first thing, we'll do sugar for starters, glucose. And I'll walk through all the steps. Glucose. Every glucose that goes in goes through glycolysis to give 2 pyruvates. That yields net 2 ATP and 2 NADHs. Each pyruvate goes to an acetyl-CoA, so we get 2 acetyl-CoAs, giving us 2 CO2s at this point, and 2 NADHs, 1 for each one of them. Each acetyl-CoA goes through the citric acid cycle, so we get 2 times the 3 NADHs, 2 times the 1 FADH2, and 2 times the 1 ATP. So when I sum all of this up for glucose, I am going to end up with 4 ATP directly. I am going to end up with 2, 4, 6, 2 and 2 make 4, plus 6 makes 10 NADHs, and 2 FADH2s. Okay, now I'm going to apply the yields from the electron transport chain and oxidative phosphorylation here. So for every NADH, I will get 3 ATPs. So I'll get 30 ATP here. I had 4 from here. And I will get 2 ATPs for every FADH2 that goes into electron transport chain and oxidative phosphorylation. So I will get 4 ATPs here. So as a total, I'm going to get 38 ATP molecules per glucose molecule, or moles of ATP per mole of glucose. So I need to figure out how many moles of glucose I had. I look on the chart, it says that there are 61 grams of sugar, and all the sugar is glucose. So 61 grams of sugar divided by a sugar's molecular weight, 180.2 grams per mole. Notice my units behaving themselves. I end up with 0.3385 moles of glucose times 38 moles of ATP per mole of glucose. That is equal to 12.86 moles of ATP from the sugar part. Big sugar high. Okay, now we're going to start looking at the fat. We'll start with the 16-0. I'm just going to divide that off. The 16-0. I'm going to use the method that's called ABCDE, as it makes sure we remember every step. A is activation. It takes 2 ATP to activate the system, so that's -2. B is beta oxidation, and I have number of carbons divided by 2 minus 1 rounds. Okay? And each round gives me an NADH and an FADH2. Okay? So I end up with, I would do then 7 rounds, so I'll get 7 NADHs and 7 FADH2s here. I will do number of carbons divided by 2 rounds of citric acid cycle, and each round will give me 3 NADH, 1 FADH2, and 1 ATP, just like we did for glucose down there. So I will end up with 8 rounds, so I'll have 24 NADHs and 8 FADH2s, and I will have 8 ATP. I have to take into account double bonds, but I don't have any, so that just doesn't come into play here at all. Then I have to do electron transport and oxidative phosphorylation. So I have to add up how many NADH I have. I have 7 here, 24 there. That gives me 31 NADH. times 3 ATP per NADH. So I've got 93 ATPs here. And I've got 8 FADH2 and 7 FADH2. I have 15 FADH2s times 2 ATP per FADH2. So I am going to get 30 ATP out here. And I had 8 minus 2, so I'm going to add 6 ATP on there. So that gives me 129 ATP, or moles of ATP per mole of 16.0. Now I have, it says saturated fat, 8 grams. So I have 8 grams divided by the molecular weight of that saturated fat, which is 256.42 grams per mole, okay, which is equal to 0.0312 moles times 129 moles ATP per mole of fatty acid, which gives me 4.025 moles of ATP. Okay? I am going to do the same thing now. I'm going to erase this part and do the same thing for my unsaturated fatty acid. So it was 24. 20 carbons long, 4 double bonds. It takes 2 to activate. Beta oxidation, I will do number of carbons over 2 minus 1 rounds. So I'm going to do 9 rounds. That's going to give me 9 NADH and 9 FADH2s. All right, citric acid cycle. I've got number of carbons over 2 rounds. It's 10 rounds. That gives me 30 NADH and 10 FADH2 and 10 ATP. Double bonds, I have 4, so I have to subtract 4 FADH2 for them when I come to do my sum. So now I'm going to add up. I have 39 NADHs times 3 ATP per NADH gives me, what is that, 117 ATPs from this. I have got 10 plus 9, 19 minus 4, I have 15 FADH2 times 2 ATP per FADH2 is 30 ATPs. And I have 10 ATP minus 2 ATP, so I have 8 ATP made directly. So this gives me 155 ATPs made. Now I've got to do the same math again and figure out how many moles I had. I had 4 grams. I had 12 grams of fat minus 8 grams of saturated leaves me 4 grams, which must be unsaturated. Divide by the molecular weight, which is 304.47 grams per mole. And that is equal to 0.01314 moles times 155 moles of ATP per mole of the fatty acid 20:4 gives me a total of 2.036 moles of ATP from this. Now what we have to do is add ATPs from the unsaturated fat with the ATPs from the saturated fat and the ATPs from glucose. If you add those 3 numbers together, you get 18.92 moles of ATP. All right. To put this into some kind of perspective for you, I ask you the following question. Basically, how much exercise do you have to do to burn that amount of energy off? So, I said, okay, if you burn 970 kilojoules per hour while walking, and the delta G for hydrolysis of ATP is equal to negative 55 kilojoules per mole, and you're walking at 6 kilometers an hour, how long do you have to walk to burn it off? Okay, so we have 18.92 moles ATP times 55 kilojoules per mole. We're not worrying about the signs here. We're using up this energy, so it doesn't really matter about the signs. Gives us a value of 1040.6 kilojoules, okay? Divide by 970 kilojoules per hour gives us a value of 1.073 hours of walking. And then if we simply take that 1.073 hours times 6 kilometers per hour, we end up having to walk 6.44 kilometers at a fairly hefty pace. 6 kilometers an hour is a pretty brisk walk in order to burn off one McDonald's chocolate milkshake. So that's just putting that in perspective, and that's how you do that kind of problem.